probabilities with the binomial distribution. The calculations can become long and tedious, especially if the number of trials is large. Fortunately, particularly when we have a large number of trials, the binomial histogram resembles. Often we can use a normal distribution, which is easier to work with. We can use it to closely approximate our binomial distribution. In order to do this, we need to be able to look up z-scores in a table. Therefore, we need to be able to we need to know the mean and standard deviation so that we can calculate those z-scores. The mean of the binomial distribution is given by multiplying the number of trials times the probability of success. Sorry, my equal sign did not come out really great here. Mu equals NP. Our standard deviation is equal to the square root of NPQ. Remember, N is the number of trials, P is the probability of success, and Q is the probability of failure, and we can get that by subtracting P from 1. The mean gives us the expected number of successes in N trials. In other words, if we let X represent the number of successes in N trials, that's our random variable, the expected value of X would be equal to NP. Another thing that we have to do when we use a normal distribution to approximate the binomial is we need to adjust for the fact that the binomial distribution only takes on integer values because the values represent the numbers of successes, where the normal distribution is a continuous distribution. There's something that we call the 0.5 adjustment that we do to account for this, and you will see how this works when we get to an example. Just think about the fact that your binomial distribution, if we have a histogram, so we would have a bar for 7, and we would have a bar for 6, and we would have a bar for 8. And so some of these will be shaded and some not, depending upon your problem. So 7.5 would be here. 6.5 would be here. Depending on which bars are shaded, we would use either 6.5 or 7.5 as our value. You'll see when we get to the example. Let's do one. Let's suppose that a basketball player has a 73% free throw shooting percentage. We want to find the probability that he is successful in at least 100 of his next 120 attempts. So we are going to assume that the probability of success is 0.73. So success is he successfully makes the free throw. And so then the probability of success is 0.73. What is the probability of failure? Well, we subtract 0.73 from 1, and so we get 0.27. Remember, those two have to add up to 1. What's our number of trials? 120. And X is the number of successes in 120 trials. Okay, so what we need to do, if we're going to do this with the binomial distribution, is we want to figure out the probability that we have at least 100 successes. So that means we might have 100, we might have 101, we might have 102, and what's the very most successes that we could have? 120, and that's if he makes every single one of those 120 free throws. Now, since this is a binomial distribution, We have a repeated number of trials. We're going to assume the probability is the same in all of them and that all the trials are independent. So we would need to do combination. Have 120 trials. We would choose 100 to be successful. We would take the probability of success, 0.73, raise it to the number of successes, which would be 100. Then we would take the probability of failure, 0.27, raise it to the number of failures, which would be 20. That gives us the probability of 100 successes. Then we would do it again. This time we would have combination 120, 101. We would take the probability of success, raise it to the number of successes, and then we would take the probability of failure and raise it to the number of failures. If I had 101 successes, that means I would have 19 failures. And I would have to keep doing this all the way up to 120. So I would have 20 formulas here, actually 21 formulas. That would not be very much fun. So what we are going to do is we are going to use the normal approximation. To do this, we need to find the mean and the standard deviation. So our mean is NP, so 120 times 0.73. This is also the expected value, or the number of free throws I would expect this basketball player to make successfully. So I would expect him to make 87.6 of them. And now we're going to calculate the standard deviation. So this is going to be the square root of NPQ. So the square root of 120 times 0.73 times 0.27 should get approximately 4.863. Store this value in your calculator so that you do not get rounding error by repunching in 4.86. That'll make us less accurate. We don't want to round until we get to the end of a problem, if at all possible. Okay. So now we need to use our normal approximation. First of all, we're going to do the 0.5 adjustment. Here's what I'll do. The problem is asking me for the probability that he gets at least 100 free throws. At least 100. Okay, since it's at least 100, we want to include 100, but we do not want to include 99. I'm going to draw myself a little mini histogram here. I don't care how tall the bars are. I'm going to draw one for 100, and then I'll usually draw the neighboring bars. I'll draw the one for the number directly above and another bar for the number directly below. Now, since it says at least 100, that means I'm going to shade the bar for 100, but not the bar for 99. So I'm going to shade all this and shade everything off to the right. Look for the color change. The color change is at 99.5. So that's the number that I'm going to use. If you use 100, you will not be as accurate. The reason we have to do this adjustment is that we want at least 100 to be different from more than 100. The 0.5 adjustment lets us account for the fact that these two things are different. If we had more than 100, we would shade the bar for 101, but not for 100. In that case, our color change would occur right here at 100.5. Okay, so let's draw a sketch, just like when we do a normal distribution problem. I'm going to shade the area that I want, my mean, is at 87.6. So 99.5 is off to the right. And I want everything to the right of 99.5. So how am I going to get this? Okay, I'm going to remember that the normal distribution is symmetric around the mean. So half the area will be everything to the right of the mean. And if I take that and I subtract the area from 87.6 to 99.5, I will get the area that I want. Okay, areas like this last one are what we can look up in the table. Okay, so we need to figure out how to get to the area that we want, which is the tail end to the right of 99.5, by using only areas that show up in the table. This is how we're going to do it. So what we need to do then is we need to find the z-score for 99.5. So we'll do x minus the mean divided by the standard deviation. 99.5 minus 87.6 divided by about 4.863. You should use the number that was stored in your calculator for that standard deviation. And you should get about 2.45. If your table only goes to 2 decimal places, that's what you'll round to. Okay, so now we're going to look up that z-score in our table. And we will find that we get an area of, I'm calling that A1, and my area is 0.4929. So now I calculate the probability that I want. My probability that my binomial variable is at least 100, so that means I have 100 more successes. This is about the same. Now I haven't defined y here, but let's think of y as being the normal variable that we are using to approximate it. So this is approximately the probability that y is greater than 99.5, which is the probability that z is greater than 2.45. In other words, that we're more than 2.45 standard deviations above the mean. And so this is going to be 0.5 minus A1 as shown in my sketch. So 0.5 minus 0.4929, which is 0.0071. That's the probability that our basketball player makes at least 100 of his free throws. Let's do another example. Let's suppose that the probability of a heart transplant being successful is 0.7, and success is going to be defined as having the patient survive at 1 year or more after undergoing the surgery. 100 patients have been through such an operation. We're going to use a normal distribution to approximate the probability that fewer than 75 will survive a year or more after the operation, and that between 80 and 90 will survive a year or more. Okay, so the first thing that we need to do is we need to figure out our number of trials. There are 100 patients. Each one can be considered a trial. The probability of success is 0.7. The probability of failure, we subtract the 0.7 from 1, so we get 0.3. Keep in mind we're going to be assuming that the results of each trial are independent of all the other trials, and that that probability remains constant across all the trials. Now we need to determine the mean and standard deviation. So the mean, or the expected value of the binomial distribution, is n times p. So we take the number of trials, which is 100, multiply by the probability of success, which is 0.7, which is 70. Another way of saying this is that we would expect 70 people to survive out of the 100. Our standard deviation will be the square root of NPQ. So the square root of 100 times 70 times 0.3. Sorry, let's make that 100 times 0.7 times 0.3. And so that'll give me the square root of 21, which is about 4.583. Be sure you store that number in your calculator so that you can use it later without having to punch in a rounded answer, which is not accurate. Now we want to figure out our 0.5 adjustment. So what I will do is I will draw myself kind of a mini histogram. And I guess here we are now on part A. We're looking at the probability that fewer than 75 will survive a year or more. So I'm going to draw a histogram bar for 75, and then I'll draw one for just over 75, so 76, and then one immediately before it, 74. Now you need to determine which of these bars will be shaded. We want fewer than 75 to survive for our part. So fewer than 75, that means 74 would be shaded, but not 75. So 74 and everything to the left. Now what we do is we look for the color change. Where's the color change? It's at 74.5. If it said 75 or fewer, we would have also shaded the bar for 75, which would have put our color change in a different location. It's important not to guess on the 0.5 adjustment. Draw yourself a sketch so you can get the color change in the right place. Now let's sketch out what's happening with our normal distribution. The area that we want, our mu is 70. The area that we want is everything from 74.5 to the left. So we want this area. But we don't have areas like that in our table. So we need to write that in terms of an area that we do have. So we do know that from our mean to the left is exactly 0.5 because our normal distribution is symmetric. And then if I take the area between 70 and 74.5, if I take this area and add it to the previous one, to the 0.5, then that's going to give me the area that I want. So I'll call this A1. So now we need to calculate our z-score. So our z for 74.5, remember we take x minus mu divided by sigma. So that gives me 74.5 minus 70 divided by 4.583. Make sure you use the stored value that's in your calculator rather than repunching it. You should get approximately 0.98. So that means we are almost one standard deviation above the mean. So now we look up our z of 0.98 in our table, and we get an area of 0.3365. So that if x is the number of successes, what I want is the probability that I have fewer than 75 successes. So x less than 75. Okay. If we let y be the normal variable that we're using to approximate the binomial. So this is going to be about the probability that y is less than 74.5. That's the probability that z is less than 0.98. So that will give me 0.5 plus my a1, so 0.5 plus 0.3365 gives me 0.8365. Okay, so now we want to look at the second part, which was that between 80 and 90 inclusive survive. Okay, the first thing that we need to do is look at our 0.5 adjustment. So 80 and 90 are the significant numbers of successes mentioned in the problem, so I'm going to draw a little mini histogram that includes those and includes the ones right next to them. So near 80, I'm going to draw a bar for 81 and for 79. Over here near 90, I'm going to draw a bar for 90, for 91, and for 89. Okay, between 80 and 90 inclusive, that means that the numbers 80 and 90 need to be included. So what bars do we want? We need to include the bar for 80, and then here everything in between, and we're going to go up to, and we're going to include the bar for 90. So then we want to look for the color change. Okay, where's the first color change? It's going to be here at 79.5. Now where's the second color change? Just to the right of 90. So here we end up with 90.5. So that means we're going to run our normal curve from 79.5 to 90.5. Those are going to be the areas that we want. So let's sketch it. $70 is here in the middle. That's our mean. That has not changed. And then 79.5 is here. Let me make my picture a little better here. And then here is my 90.5. The area that I want is everything in between. So how do I get an area that looks like that? Well, I'm going to have to take the area for 90.5. Okay, so keep in mind 79.5 is in the middle. I'm going to take the area for 90.5, and if I then subtract the area between 70 and 79.5, then I'll have it. Okay. Okay, if I take this larger area and then subtract the area between 70 and 79.5, I should have the area that I want. So I'm going to call these A1 and A2, and I should be able to find those in the table once I find my z-scores. So now I want to find the z-score for each of those x values. So z for 79.5, I'm going to do x minus mu over sigma. Actually, let's make it y. If we think of y as being the normal variable that we are using to approximate our binomial, so we're going to do 79.5 minus 70 all over 4.583. Remember, I'm using the stored value. We should get about 2.07. Then we're going to do 90.5. So this will be 90.5 minus 70 all over 4.583. This gives me 4.48. So now I want to look each of these up in the table. When I look up z equals 2.07 in the table, I'm going to get an area, and I guess this would correspond to A2 in my picture. 0.4808. Now let's look up z equals 4.48 in the table. When you do, you will find that it's off the chart. What does that tell us? Well, if you notice, there are quite a few values of z in your table for which the area is listed as 0.5000. Does that really mean that exactly that area is exactly 0.500? No, but it's very close. Everything in that table is rounded to 4 decimal places. So if we think of, remember our standard normal distribution is one in which our mean is 0 and our standard deviation is 1. If I put my z way out here, my z is 4.48, then it turns out this area is approximately 0.5. It's important to notice that the area is not equal to 0.5, because if it were, we would be saying it is impossible to be to the right of z equals 4.48, or any of those other z values that give us an area of 0.5. So we are going to use an area of approximately 0.5, but we should know that it's not equal to 0.5. To be equal to 0.5, it would have to include the whole entire right side of our standard normal curve, and there would be nothing to the right of that z value, which would not be correct. But within 4 decimal places, the closest that we can get is 0.5. So the probability that my number of successes is between 80 and 90 inclusive. It's this. This is approximately equal to the probability, if I let y be the normal value, that y is greater than, what was it, 79.5 and smaller than 90.5, which is approximately equal to the probability that z is between 2.07 and 4.48. And so this is about 0.5 minus, let me just go ahead and write these down with what my numbers that I called them. I called these A2 minus A3. So 0.5 minus 0.4808, which is equal to 0.0192. This problem is a good reminder of what we've learned earlier, which is that nearly all of the area, 99.7%, is within 3 standard deviations of the mean in the normal curve. So here at 4.48, 4.5 standard deviations away from the mean. That is very, very improbable if a variable is truly normally distributed. The normal distribution provides a good approximation to the binomial only if your number of trials is sufficiently large. There are several rule of thumb tests to decide when this is. One good one that's very easy to use is this. We're going to use a normal approximation only if both NP and NQ are at least 5. Okay, let's do an example. Can we use a normal distribution if we have 15 trials and the probability of success 0.4? So here our n is 15, our p, or probability of success, is 0.4, therefore our probability of failure is 0.6, subtracting from 1. We really only need to check the smaller one, so choose the smaller of p and q. In our case, p, and p is 15 times 0.4, which is 6, which is indeed at least 5. What about NQ? NQ, so 15 times 0.6, that gives me 9, which is also at least 5. Do you see why we only need to check the smaller one? If the small one's at least 5, then the big one certainly will meet the qualification. So therefore, we can use the normal approximation. Let's do another one. Let's suppose that we have a binomial distribution with 80 trials and probability of success 0.05. So in this case, our n is 80, our p is 0.05, therefore what is our q? 0.95. So once again, choose the smaller one, so we'll choose p, so np, that means 80 times 0.05. This gives me 4. This is less than 5, and so that tells me that no, I cannot use the normal approximation. Has to be at least 5. When you run into problems is when you have a relatively small number of trials, but your probability of success and failure are very close to the ends, close to 0 or close to 100. Here we have 0.95 and 0.05. They're very skewed. The probability of success and failure are not close to one another. So in that case, you need a lot more trials to make it a good approximation. Just out of curiosity, how many trials would we need? Okay, in this case we want our NP to be at least 5. So we don't know n, but our p is 0.05. This is smaller of the two, p and q. Divide both sides by 0.05. And so this gives you 100. So you would need at least 100 trials in order to be able to use the normal approximation to your binomial. Where when our probabilities were 0.4 and 0.6, relatively close to each other, 15 trials was enough. So it makes a big difference how far out to the end your probabilities are.